I'm going to talk about some of our work on adaptive reinforcement learning. This is joint work with my colleague Christina Liu and our PhD student Sean Sinclair. And I'll also talk about work which I've done with a wide range of other collaborators, including some amazing undergraduate and graduate students. So before I start talking about our research, I'm going to give you a simple example of the style of problems that we want to study. So imagine we were actually in New Orleans, and let's say this is Bourbon Street, and you're in charge of an ambulance, and you can decide where to position this ambulance. Now, let's say you decide to start off with this ambulance in this position, and then after some time, you get a 911 call, and then you need to dispatch this ambulance to this call. And after it's done answering to this call, you can then choose to reposition your ambulance. So maybe you decide to move it more centrally. And this is useful because maybe the next call is close by to this ambulance, and so it can respond faster. So you go there, you serve this call, and then you can again reposition the ambulance. So more formally, this is a style of sequential decision-making problem where you're a controller and you have this one ambulance which you want to position along this one-dimensional space, let's say the 0, 1 interval. And every time you move your ambulance, you pay some transportation cost. And then from time to time, you get a request, a 911 call, which is arriving drawn from some distribution. And you need to respond to this call, and you pay some cost due to the delay you incur in responding to it. And your aim is to come up with a policy as to where to position this ambulance over time, so as to minimize some combination of these costs. So what sort of questions would we like to study in this framework? Well, one thing is you don't want to design a policy which is very, very particular to one setting. So you want sort of, as I change the settings, you want to be able to have your policy adapt to the particular features of the settings that you study in. So let's say you're designing ambulance routing in New Orleans versus ambulance routing in Ithaca. The policies may be very different because of the underlying distribution of the 911 calls. And what we really want to use are approaches which are data driven. So you don't want to have a model which does not sort of incorporate the local data, but you want to use your data to try and change your policies. And there are many ways of doing this. So for example, using techniques like approximate dynamic programming or reinforcement learning, which essentially take the underlying problem, which inherit like features of the problem via things like simulators, but which also use data from past traces to try and improve their policies. The problem with these approaches are that in order to try and do well for different settings, you often make these policies extremely complex. So if you use something like ADP or say DeepRL, the underlying policy space tends to be extremely complicated. And this is good if your underlying problem is very complicated. Let's say you're using it to solve chess or Go, but in settings where your problem is much simpler, these approaches may not be able to like adapt to the complexity of the problem directly. So you may end up using an approach which is much more heavy-handed for the setting that you want to study. And so ideally what we would want is policies which adapt to the data, but also adapt to the complexity of the problem that they're being used for. In addition, whenever you use methods such as approximate DP or reinforcement learning, these are always guided by the objective function that you feed in. But like in the ambulance example, the objective function may not always be obvious. And sometimes instead of focusing on a single objective, it's better to actually understand how policies do well for different objectives and then ask a central planner to give them the trade-offs between these different objectives and ask them to choose what's the right setting of these trade-offs. So what we've been doing in our research is essentially trying to tackle some of these problems of trying to incorporate reinforcement learning and ADP approaches in real life problems. So firstly, we've been trying to understand how you can use ADP and RL approaches along with ideas from adaptive discretization such that these approaches actually adapt to the complexity of the problems that they're trying to solve. And what we've shown is through a series of papers that you can use ideas from adaptive discretization to actually improve the performance of most reinforcement learning algorithms such that you get the same performance but with much lower memory and data requirements. Next, switching to this question of multi-objective reinforcement learning, what we have started looking at is different ways of understanding trade-offs between different objectives, and in particular, what are the information theoretic limits of control for different objectives. And this becomes particularly important in problems where you're worried about constraints such as equity or fairness of objectives of rewards across different agents. And we've been trying to understand what are the limitations of using RL in these settings and how you can adapt RL policies to actually understand its performance across a wide range of objectives. Um, but more importantly, when you try to use these approaches in practice, one problem that often comes up is because these algorithms are very, very different, it is often difficult to compare them or compare two different algorithms in an apples to apples basis. Um, so for example, it's tough to try and understand how, say, a simpler policy compares to a much more complicated, say, deep reinforcement learning policy. Um, for the second one may do almost as well, but it's using much more memory and much more data. And so the third thing that we've been trying to do is take all of these problems, so in particular problems arising from operations research from like real life settings, and try to build benchmark suites around them. So particularly we've built a backend where we have a bunch of benchmark problems, and we also instrument them so that if you want to test a new algorithm, you basically write it in a particular input output format, and the backend essentially generates, like, compares your algorithm with other algorithms and compares it along a wide range of objectives, including how much memory does it take, how well does it generalize, how much data is required, etc. And so in this talk, I'll primarily talk about our efforts in using adaptive discretization in reinforcement learning. Um, but towards the end, I'll also try to give some sense of the work we're doing in multi-objective settings. All right, so here is the basic reinforcement learning problem. So the idea is that there is some underlying environment which represents the real world, and then you have an agent which is the controller with its policy. Now, the agent starts off with some initial state, and it decides on some action to take at each time, depending on the current state. After which the environment then updates the state based on the on the current state and the action, um, and then generates a new state as well as a reward from some transition matrix. So in the case of the ambulance routing problem, the initial state could be the starting location of the ambulance at the start of the day. The action at each time could be, where do you want to position the ambulance based on its current position? And then the environment can generate a new 911 request, upon which the ambulance has to go and meet the request, and it'll incur some cost due to both repositioning as well as the delay cost in meeting the request. And the particular flavor of reinforcement learning that we'll be considering for the rest of this talk is what's called on-policy episodic reinforcement learning. Episodic essentially means that we're going to be looking at this problem over a horizon of some 8 steps. So think of this as 24 hours in the case of the ambulance. But we're going to repeat this 24-hour episode over k times. And what on policy means is, in order to measure the performance of our algorithm, we will try and see how well it does in each episode compared to the optimal algorithm. So in particular, we're going to characterize the performance of any algorithm through its regret, which is the additive difference between how well it does and the optimal algorithm summed up over all episodes. So episodic RL algorithms come in many flavors, and even though our approach can be used for all different types of RL algorithms, for the sake of this talk, I'm going to focus on one particular simple policy, which is something called Q-learning. So what happens in Q-learning is you try to come up with a function called a Q function, which is a function of both the state and the action, and which essentially tries to characterize how well you would do in a certain state X if you played an action A. And then from the next state onward, you played some policy pi. So this pi, you can think of this as a reference policy. If you follow whatever this reference policy is suggesting, then the Q function for state X and action given by the policy is known as the value function. But in general, the Q function is the reward if you take the current action followed by the value function of the next state. And in the case where you're using the true optimal policy, then the value function turns out to be equal to the max over all actions of the Q functions. And this is what's called the Bellman equation. So what Q-learning does is it tries to approximate the Q function for every state and action based on data. And then whenever you're in a certain state and you need to decide what action to play, you always play the action which maximizes your proxy for the Q function. So this method works extremely well if your underlying space is small. So let's say it's some discrete space and you have a finite set of states and a finite set of actions. But this becomes much more challenging when you have much larger state and action spaces, in particular if, say, your state and action spaces are continuous, like was the case for our ambulance example. So in this case, what you need to do is you can still use this approach, but you need to assume that your underlying Q function has some kind of regularity. So for example, let's say your underlying function is Lipschitz smooth. And once you do this, you get this whole spectrum of policies where on one end, you can have parametric policies. So you can try and approximate your Q function using some basis functions. So for example, a linear basis functions or neural networks. And these methods tend to work extremely well, but they always have the problem that they work well as long as your Q function is well approximated, is close to the span of the basis that you've chosen. But if that's not true, then there are no guarantees. On the other extreme, you have non-parametric methods such as nearest neighbors or kernel methods, and these tend to always work well as long as you have enough data. So you'll always get a good approximation for your value function and your Q function, but this may be expensive in terms of memory and samples. And the approach I'll talk about is kind of the extreme form of a non-parametric approach where we are trying to approximate a Q function locally in each piece by some piecewise function. So in more detail, suppose I have a continuous Markov decision problem. One thing I can always do is I can take this problem and then discretize it using an epsilon net. So for example, in the case of the ambulance on the 0, 1, I can take the space 0, 1, the state space and the action space and discretize the continuous space into a bunch of squares. And so now I get the square grid. And once I have this, I can now use Q-learning over this discrete space. So these sort of uniform discretization methods actually turn out to work well in the worst case. So in particular, this can be shown to be worst case optimal. However, in practice, this is not a very good policy because it creates a sort of unnecessary exploration. You need to explore all parts of the space and you're not taking advantage of any structure that there could be in the space. So how can you take advantage of the structure? Well, here's an example. So suppose this was your underlying Q function. So somebody has calculated it and you can see that this green is a high reward, the red is a low reward. So for any state you want to sort of play the green, an action corresponding to the green region. So this would be the optimal policy in this case. Now, you don't know this Q function and you want to somehow try and discover this optimal policy. So suppose you start off with an epsilon discretization, but let's say you use a very coarse discretization. So maybe you just discretize the state space and the action space into greater than or less than 0.5. So you have these 4 buckets. And over time, as you observe data, you can come up with some sort of estimates for the Q function in each of these buckets. Now, whenever you get a certain state, so suppose your state is xt, what you can now do is look at all buckets which contain xt, so which are these 2 buckets on the left, and then try to pick the bucket which has the highest estimate for the Q value, the stop bucket, and now you can play any action corresponding to this. So this would be the basic idea of doing Q-learning on a discretized space. And as you get more data, now you can sort of update. So instead of 1.7, once you get more data, you can update the Q value. And this, what we want to do is we want to take this, but we want to now somehow learn a better way of discretizing the space. And the natural idea is, well, you can look at parts of the space which seem to have very high rewards and then try to split them up into more finer buckets. And that's essentially what we do. So essentially what we try to do in our policy is look at regions and try to, and where the statistical uncertainty is roughly equal to the diameter of the region, and then subpartition that region into new buckets, which now inherit the Q function estimates from their parents, and then continue this process. And ideally, what we would like is, as we continue this process, the discretization starts looking something like this. So it zooms in on the regions where the Q function is high and is small, and is coarse in regions where the Q function value is small. So does that happen? Well, here's an example of using our policy in practice. So this is for the 1D ambulance case. And what you can see on the left is we are comparing our policy, which is in red, in green, along with the optimal uniform mesh policy. So the optimal Q-learning policy using a uniform grid. And you can see that both policies started off with the same rewards, but as the number of episodes increases, the adaptive policy very quickly finds something close to an optimal solution, whereas the uniform mesh takes a long time to find the same value. And on the other hand, even after it's found a value function or a policy which is near optimal, you can see that the adaptive policy is using way fewer partitions, so way less memory compared to the optimal policy with a fixed partition. And pictorially, you can see the behavior in this plot on the right, where over time, we are discretizing the space more and more finely, but the algorithm is only discretizing in regions where the Q function value is high. Remember, the algorithm does not actually know the underlying Q function. It's automatically trying to figure this out based on the data that it sees. So formally, what you can show is policies of this sort, as long as you do the adaptive discretization carefully, they are optimal in the worst case. So they're optimal in a min-max sense, but moreover, they're also optimal based in spaces which are much smoother than the worst case. So in particular, you can show that the regret of these sort of adaptive discretization policies depend on what's called the zooming dimension, which is a measure of the complexity of the underlying space. So in short, what these policies do is they tend to adapt to how difficult your problem is and perform better when your problem is easier. On the other hand, if your problem is difficult, they will still perform as well as the optimal policy with fixed discretization. So this was our attempt at trying to improve RL policies to be more adaptive to the complexity of the underlying problems. I just talked about Q-learning, but you can actually use these kind of approaches in much more complicated model-based RL algorithms. But in the rest of the talk, I want to briefly talk about our attempts at actually making it easier to compare these different policies. And this, for any of you who have tried using reinforcement learning in practice, you'll know that this is actually really challenging. So whenever you have a real problem and you try using policies that other people have come up with, it's often difficult to understand how well these would perform. So in particular, how much memory they would need, how much data they would need. Usually, if you look at when people report the performance of these policies, they will just talk about the final performance, but not all of this that goes in under the hood. So what we've been trying to do is come up with a set of benchmark policies drawn from real life instances such as ambulance routing, vaccine allocation, ride sharing, etc., where we basically build the backend simulator for these problems and also the instrumentation such that you can take different policies and try to compare them on a like to like basis. So essentially we specify the input output requirements for these policies, and then we do all the backend processing in terms of simulating the policies, collecting all the scores, and then actually comparing and displaying these different policies. So here's an example of using the OR suite for the ambulance routing problem that I was talking about. So this was work done by a senior undergraduate student, Carrie Rucker, where what she did was she enabled a bunch of different environments. So the metric environment was the one I was talking about, where the ambulances are in Euclidean space. So you can have K ambulances in say 0, 1, or you could sort of generate the underlying world from based on say an OpenStreetMap. So here's an OpenStreetMap for Ithaca, and we have actual data for 911 calls in Ithaca, and we can sort of convert this to a large network and then try to use these policies on this network. On the left, you can see we have sort of run different policies. So the policy that I talked about was ADA-QL, but we are also comparing with things like policy optimization methods, other sort of stable baselines which people have come up with in practice, as well as simpler heuristics such as just looking at the median. And we can compare all of these policies for the performance for a particular objective, but also compare them for different objectives at the same time. So what was their query time, how much memory did they take, how did they do for different objective functions. So that's all I want to talk about in terms of our work. I'd be very happy to sort of collaborate more with any of you. If any of you are interested in sort of using the OR suite and things that you do, that would be really exciting for us. But I do want to sort of conclude with my heartfelt thanks to Kishan. A lot of the research that I talked about was influenced a lot by things that he suggested that we do, where he was sort of talking about not just focusing on the theory behind these algorithms, but trying to understand how these could be used in practice and how other researchers could could sort of take advantage of the work we are doing and try to incorporate it in their research. So was really looking forward to sort of telling him about the work we've done and getting more feedback from him. But in any case, thank you, Kishan. Thank you for everything.